So, hello everyone, Cosimo Lupo from INFN, and today we'll talk to you about target-based learning and hierarchical imitation learning through burst. So, we implemented a recurrent neural network by exploiting pyramidal neurons in which we have dendritic segregation and many compartments, among the others. So somatic compartment, which receives the input from the sensorial input, and two apical compartments where we have the recurrent connections from the other neurons, and the apical distal compartment where we receive signals from other areas of the cortex or also contextual informations, contextual signals. And this architecture allows us to implement this coincidence mechanism, also seen in from data by Larkum, for example, in which the somatic spike can open a window of some tens of milliseconds. And if we also have an apical coincidence spike from the apical compartment as a confirmation, this time window, instead of a single spike, we have a high-frequency burst of spikes. And we can use these bars to encode the activity of the network, and for example, let the network achieve some task. So we can encode, as I said, some output as a spatiotemporal pattern of bursts, and we can change this pattern by implementing this plasticity rule that is derived through a maximum likelihood approach, that in practice means aligning the apical spike from the spontaneous activity and the target activity when the somatic window is open. So here we can see how, for example, a simple store and recall task can be reproduced. In this case, it is a 3D trajectory. But also we can we can solve some more complex tasks. For example, a navigation task in which the agent has, first of all, to reach some button, unlock it, and then finally reach the food, the reward. So in this case, this complex task can be decomposed into a set of sub-policies. For example, first decide which target go toward, for example, either the button or the food, and then actually implement the navigation. So this can be done by hierarchically organizing the network itself. So we can have a higher layer of the network, which is the manager, and the lower layer of the network, which actually implements the motor actuation. So the high network decides the main policy and gives this output as a contextual signal to the motor actuation. So this hierarchical architecture can provide very good performances. In this case, for example, we have a reward on average of 9 out of 10. And with a success rate very high, and also this hierarchical decomposition can be applied to even more complex tasks. If you want to know more, you can go have a look at my poster number 13. Then also attend the talk by Cristiano Capone tomorrow, and also finally have a look at our archive paper that has been recently accepted in ICML. That's it.